Hello, my name is Michael DeLuca, and I work as go-to-market manager in ON Semiconductor's Industrial Solutions division. And I'm happy to have this opportunity today to talk about image sensors and the use of CCD and CMOS technologies in industrial markets. The discussion of these technologies can sometimes be very contentious. So often this discussion seems to turn into a battle with people trying to determine which technology is better, which one is the winner. And I think this is human nature. Whenever people see two things, they're always looking to see which one's better, which one wins, whether it's sports or technology or movies or ice cream flavors or whatever's being compared. And the problem, I believe, is that this is not always the brightest way to think about things, because what is good for many things or for many people is not always what's best for all. This is a perception that I think we have, that if something works in many applications, perhaps it can just be applied everywhere. It can be used as a single solution for everything. So this is what I'd like to talk about, to understand if this is truly the right way to think about these technologies, or if perhaps instead of this fight, there is cooperation, and that there are opportunities for both of these technologies to exist depending on the particular application that's in question. Now, if we do think about this as a battle, we can look at what we know, or at least what we think we know about these two technologies. CCD is the former champion, but now is old and is tired, and it can't keep up with the new advances that are coming in the new technologies. And CMOS is new and it's exciting and coming on strong, and maybe it's already won the battle. But is this right? Is this real? I mean, is this the tale of the tape as I have this slide, or really is this the perceived tale? And it's just the perception that we hold here. Because again, what's best in one application might not be best or more appropriate in all. So let's look at some information. This is what we know or we think we know here, but let's look at some information and some data. Now, this slide has some information from the market research company TSR and looks at sales of CCD and CMOS devices by unit volume into all markets. Now, looking at this slide, it's really clear CMOS just dominates in terms of the number of units that's sold here. The right side of the slide presents the same information, but it's shown here in a percentage basis and just showing the very top to kind of give a scale of what's going on. And you can see that the CCD devices are less than half of 1% of units being sold into all markets. I mean, looking at this slide, you can even ask why we're talking about this at all. But looking at all markets can be deceptive, because in this discussion, all markets include cell phones and tablets and drones and so many other areas where CMOS devices really are dominant. So if we're going to go and look and think about this in terms of industrial markets, it helps to take this data and zoom in just to look in that one area to get a better understanding of how this CCD CMOS split plays out there. Now, this shows some information that comes from AIA and looks at the split of CCD and CMOS unit sales just into machine vision markets. This looks a little different than what we just saw, and you can see that there are many more CCD devices that are being used in this market compared to the world as a whole. But there's also no question that the trend of the use of CMOS devices in industrial markets is growing very clearly. And if you think about it, the reasons for this growth are very clear. CMOS has so many strong advantages that it can bring to the imaging needs of this type of market. It has great advantages in bandwidth, where it works with digital outputs and is able to process and move information very quickly to get it off of the sensor and into the camera electronics. CMOS is highly configurable in terms of its operation, and can access different regions of interest that capture only one portion or multiple portions of a scene as needed, and you can move those around dynamically during capture depending on the particulars of the application. There are power advantages that CMOS can absolutely bring in terms of working in low power configurations, even while maintaining high frame rates. Processing of an image can be done directly on the chip, so you can have a CMOS device that provides not just a digital signal, but a complete finished JPEG file, or an H.264 video stream, or whatever, coming directly from the sensor. And you can tune and customize the device by working with a number of different registers that allow the operation to be customized and modified and optimized for the specific end-use application. Now, at ON Semiconductor, we have a full portfolio of devices that work with these high-performance capabilities because they're based on CMOS imaging technology. Our Python family of devices ranges in resolution from VGA up through 25 million pixels, with a global shutter design that allows moving images to be captured without the addition of motion artifacts to the image. These devices provide excellent image quality, but also provide very high bandwidth, as you can see in the graph here on the right, with speeds available from these devices that are twice the speed of 10 gig E or twice the speed of USB 3.1 in terms of their operating conditions. So there are a number of opportunities that are available from the performance that comes with this technology, and you can even take this performance and modify it and adjust it or customize it based on the performance that's needed for a particular application. Working, for example, with very small optical formats like the new Python 480 or the ARO 135 devices, or modifying a design so that the same imaging performance is available at a lower frame rate, like some new options we have with our Python 1300 or 5000 devices that make this high performance imaging available now at a more cost effective level. And with all of these capabilities, CMOS devices are being incorporated everywhere into so many different uses in industrial imaging, whether it's traffic or motion analysis or robotics or scanning or inspection. And then even outside of industrial markets, right, the imaging performance and flexibility that's available from CMOS technology makes it used today in so many different areas, in tablets and security cameras and automotive ADAS systems or drones, even professional cinematography. On semiconductor CMOS image sensors are used in Alexa digital cinematography cameras that come from ARRI. And these cameras are used throughout the motion picture and television industry for any number of different productions. In fact, the last 5 winners of the Academy Award for Best Cinematography were all shot using an Alexa camera, which uses a CMOS image sensor from ON Semiconductor. So the next time you go to see a movie in a theater, there's a really good chance you're watching a feature that was filmed using a CMOS imaging device. So the uses of CMOS devices are so wide, they're so broad. I mean, why do we even spend time talking about other options or other technologies? Well, as we've said before, CCD is the old champion, right? If you want to use that language, it has the performance that so many people are familiar with and comfortable with from working with this technology in the market, but it still brings advantages out in terms of the way it performs. The resolution that CCDs can provide, provided with the image uniformity that's critical in so many applications, being able to work with a very clear, very uniform image is a strong advantage that CCD has to play. Being able to work in the charge domain, which provides different opportunities and different capabilities than what's available when working in voltage, which is a characteristic of CMOS devices, right? The ability to work with very long integration times with very, very low dark current. We have CCD devices that are used by customers in astrophotography with 30-minute or 60-minute exposure times to allow photons to integrate over this long time without building up a dark current signal that would otherwise degrade the image. And CCD devices incorporate analog tuning, being able to design and customize the exact construction of the camera specifically for the use and the application that's being addressed. Now, a good example of all this is our 47 million pixel CCD. This is an interline transfer device with a global or electronic shutter integrated directly into it. These devices are used today in flat panel inspection. Today in flat panel inspection, in critical end-of-line inspection steps that are required for these flat panels. And our customers come to us saying that they would very much enjoy the opportunity to work with CMOS devices to take advantage of the benefits they provide. But today, CMOS devices do not provide the performance that they require for use in this application. They come to us and say, we require the image quality that CCD can provide. And so we're very excited to be able to go and provide the highest resolution interline transfer device that's available on the market, this 47 meg device. Another example of the type of performance that's really unique to CCDs is electron multiplication. This is a family of devices that we have that are based on interline transfer CCD design, but incorporate an electron multiplication step into the amplifier as well. This multiplication happens in the charge domain. It's not possible to run an electron cascade in voltage. So we take the electrons before conversion to voltage and run them through an electron cascade to multiply the signal, to increase the magnitude of the signal before the actual measurement's made. So we can get 10 or 20, up to 100 times multiplication of these very low signals, which allows the device to operate with sub-electron read noise. Now, this intrascene switchable gain that's listed here, this is very compelling in that it allows the device to switch dynamically between this high gain EMCCD output and a standard CCD output. So in a low light scene that has a bright component in it as well, you can see, like here, a traditional sensor is able to see the bright part of the scene, but the very dark parts are beyond the noise floor of the device. And if you go and work with a traditional EMCCD device, before you can increase the gain high enough to see the information in the shadows, you start a cascade in the electron multiplication channel that then blooms and destroys the integrity of the image. But with this intrascene switchable gain, with this switch that's in place, you can take the bright part of the image and run it only through the standard CCD output, and then the dark parts of the image, and then run them through the electron multiplication output. And then the system can respond dynamically as lighting conditions change by combining these two sets of information. This is a really compelling technology that's of great interest in low light applications that can have a bright light component, such as a traffic that might have a street lamp or a headlight in the scene, or in medical applications where you're looking at something on a slide that's fluorescing, or in ophthalmology, or even very obviously in a security or a defense application where you want to look and see into a dark shadow or into a dark corner while there's a street lamp that's also into the scene. So with these different types of technologies, CCD image sensors are used today, again, in a number of industrial applications. If you look at this slide, it looks really similar to the one that I had up before. There's still inspection steps that are in here that are done with CCDs. There are still traffic applications that are done with CCDs. So it really then becomes a question of where on the spectrum a particular application lies in terms of understanding what the right and best technology is to use. Now, outside of the industrial space, there are another set of applications where CCD technologies really provide really interesting and very compelling advantages. A recent example is the satellite that's here. This is the WorldView 4 satellite that launched late last year, late in 2016. This satellite from Digital Globe takes pictures of the Earth from orbit and is used for monitoring deforestation or results of natural disasters or developing images that are used for urban planning or growth. This WorldView 4 is the latest satellite from Digital Globe. It includes image sensors that we developed in conjunction with Harris Corporation, which put together the imaging system that's used on the satellite. So this again becomes another CCD application because of the performance that this technology can uniquely provide. So in the end, it really becomes a question of understanding the fact that there's really no one technology that's able to cover all performance vectors fully. I mean, there are some technologies or an implementation of a technology even where you might have an advantage in resolution, but not in power. Or you might have an advantage in sensitivity, but not in bandwidth, or whatever else, whatever other performance vectors that are appropriate to put onto the screen here for the application that you're working with. The coverage that you're talking about can change whether you're talking about one technology or another, or within a technology, how you work with the particular implementation. So that in the end, we're really in a situation where one size really doesn't fit all, right? One technology doesn't really fit everything, right? The needs of the different applications are going to differ by the technology, by the implementation that's in there. And in our image sensor portfolio, this fact is really reflected by the breadth of the devices that we have available in our portfolio. If you go and look at ON Semiconductor's image sensor portfolio, you can see that we don't have one CMOS device. We have a whole family of CMOS devices where one might be more appropriate than another depending on the particular imaging characteristics that are needed for a given application. Perhaps it's general purpose imaging that's needed, or perhaps it's high-speed imaging or radiation hardened imaging so that the image sensor retains its imaging performance in high radiation environments such as outer space or even in a nuclear reactor. And in a similar manner, we have a variety of CCD image sensors, whether it's based on interline transfer or full frame devices or linear or devices with electron multiplication, all because they have different features and different advantages to them. And then for all of these, there's a whole nother level of customization that's available as well in terms of pixel size, which moderates the sensitivity and resolution that's available from the device, or the color filter array in terms of monochrome or color or customized CFA patterns, or near IR sensitivity or cooling capabilities, or the cover glass, or any of a number of other variables. There are all these different options that are available because in the end, one device, one technology, one size really doesn't fit all applications. So the way that we really look at this in ON Semiconductor is that these two technologies have advantages. It's not that one is better than the other, but that each is different. Each brings its own strengths to the table. CCD has some advantages. CMOS has some advantages. And there are some applications that fit well into one category or fit well into the other. But to be honest, most of these industrial applications span this space, with some parts of an application being associated with one technology and some parts being associated with another technology. And the exact match depends on exactly what it is that you're trying to do with the application that you're working with. And that's why we feel it's so important to have a broad portfolio that's based on both technologies, giving customers the opportunity to select the best product for their application, regardless of the underlying technology that's being used. That's also one of the things that's so exciting about the work that we are able to do inside of ON Semiconductor because of the acquisitions that we've recently put in place that bring expertise into the company from so many different areas, whether it's large format CMOS or small format or small pixel or CCD or full frame. All of these different imaging technologies are now within our image sensor business unit because of all these acquisitions. We have the opportunity to work across all these organizations to leverage these technologies and products and the people to go and bring better products and better devices out to the customers that we serve. And so if we go back to where we started, we talked about this battle, this perceived battle between CCD and CMOS and which one will win and which one's better. And really, I believe that that's the wrong question. It's critical to ask the right question as you go and start thinking about the use of different image sensors and the different imaging technologies in the work that you're doing. It's easy to say which technology is the best, but I really think that's the wrong question. The right question, I think, the one that you really want to ask is, which is the technology that's best for my application? And as I've gone through this discussion and listed some of the performance vectors associated with the different technologies, you might listen and say to yourself, oh, this is very clear, right? From the way that these are described, there's really only one technology that's the right one for the work that I'm doing. And that's great. That's fantastic. The problem is that someone else listening to this discussion is going to say exactly the same thing, but come to a different conclusion because they're working in different markets or different applications. And so that's why it's so important to have this breadth of products, this breadth of technology to be able to meet and address the different needs of people throughout the entire market. It's easy to say which technology is the winner, but again, I think that's the wrong question. The right question is, which is the technology that will make me the winner, that will allow you to meet the needs that you have for the imaging applications you have in place. So I encourage you, as you think about this question, don't think of it as a battle. Don't think of it as CCD or CMOS. I truly believe that this is and, not or, and that you now have this wonderful opportunity to go and choose across this broad portfolio of devices with different technologies to find the one that matches best to the particulars of the application you have, so that all of us have the opportunity now to move forward with success. Thank you.